Okay, so let's get right to it. We're told that we're given string 1, string 2, m and n, the length of string 1 and string 2 respectively. And we want to output the minimum distance from string 1 to string 2, right? And the reason we're working with pointers, once again, I'll remind you, is because if we want to keep splicing the string and creating copies of the string and sending copies of the string around, that kind of blows up our space, right? So instead of keeping copies of the string, we just keep copies of pointers to the end, to the last part of the string that we want to consider, right? Um, and yeah, as I mentioned earlier, we're taking an outward in approach. So we'll always try to match up the last character of these strings, right? So let's get started. What happens when our last characters match, right? We want to compare string 1's last character to string 2's last character, right? So when these match, we just kind of want to cancel these out, and then we just want to run our algorithm on the remaining strings, right? That's snow and sun with a double N. So let's write that out. If our stir 1 m is equal, oh sorry, m minus 1, because m is the length, so is equal to stir 2 m n minus 1, then what do we want to do? Then we want to return the edit distance naive on the rest of the strings, right? We just want to return, let's say like the last two characters match up, so now we just want to run it on the rest of the two strings. So that's on stir 1, stir 2, but now we only want to consider up until the m minus 1th index, not index, up to n minus 1 characters of string 1 and n minus 1 characters of string 2, right? Yeah, so that's another base case handle for us. Now basically we want to see that out of these three operations that we're given, right, which of these three operations can we do in this iteration of edit distance naive that will lead to the minimum number of operations going forward, right? So we need to test out all three. So we'll call these insert, delete, and replace, right? Now, what happens when we insert a character? All right. So let's say we're working with snow and sun. Let's say we're working with snow and sun. Our m is 4, our n is 4, right? When we're inserting a character, we will be assuming that we'll be inserting a character that is the same as the last character of string 2, right? This is string 1. This is string 2. So if we're inserting a character in string 1, we want it to be the last character, right? Because as we said, we're matching up last characters. So that means that then after doing that, we only want to consider the edit distance from, after doing that, we want to consider the edit distance from string 2, m minus 1, no, sorry, m, because we still have working with the same m, right? We're still working with snow, but we already matched up that last character n of string 2. So that's why we'll run it up to n minus 1 characters of string 2. Similarly, for a deletion, let's see what happens when we try to delete a character. Now we'll be assuming that we're deleting the last character, right? We're always going to be, whenever we're deleting, since we're matching up last characters, we'll be deleting our last character. So now we want to know the edit distance from m minus 1 characters of string 1 to all n characters of string 2, right? Because string 2 remains untouched. And similarly, I'm pretty sure you figured it out by now, but for replacement, what we do is we matching up, we're replacing w with the last character of string n, right? So we're replacing last character of string 1 with last character of string 2. And so then we only want to consider up to m minus 1 characters of string 1 and n minus 1 characters of string 2. And yeah, that basically gives us it. Now all we want to do is we want to return the min of these three, the min of insert, delete, and replace. But we also need to keep in mind that these three operations took a certain operation themselves, right? So each of these three operations did take like some certain amount of space themselves, right? So we want to add a plus, took one operation themselves, right? So we want to add that +1 to sort of factor in for this particular operation. And yeah, that gives us our edit distance naive. Let's run this together. Oh, I just realized I didn't run my test cases, but yeah. Here, let's run this together. So you see that it has given us the correct output. It only took 2.01 milliseconds to run. It seems sort of efficient, but let's run it on the large word and let's see how long this takes to run. Okay, so that has taken 10 seconds to run. It has given us the expected answer, that is 13. But it also took 10 seconds to run, right? Which is a lot just for two strings that have an edit distance of 13. So we somehow need to now understand that we understand the need for a more efficient approach to solve this problem, right? And that is exactly what we'll be writing out an edit distance. And what we'll see is the beauty of this algorithm is that it's just one small modification, just one small tweak that you can make that makes this algorithm like so much more efficient. And we'll talk about that in the next video.